Click the bell icon to get latest videos from Ekeeda.
Hi guys, today in this particular video we will start the next analysis, that is CG amplifier AC analysis of FET. Now in this CG amplifier common gate characteristics we will try to prove in this particular analysis. Let's see how it works. Now in this circuit, I have one resistor, that is RD, which is connected at the drain side. At the source side, I have resistance RS, which is connected in between minus VSS and the source side. If you look at this particular circuit, you will get to know that I have applied input at the source side and I have applied output at the drain side. So, gate terminal is neither connected to input nor at output. So that's why this circuit is called as CG amplifier. Many a times in the numerical, you will not get this orientation of the circuit. You will get something like this. Something like this you will be getting, and here this is your RD and this is your RS. Few more resistance also will be there, but no need to worry about the orientation. Whatever we have usual orientation, stick with that particular orientation only, so that your AC analysis will become very simple as per the steps. We will follow the steps of AC analysis of CG amplifier so that things will become simple. First and very important step is keep short circuit of all coupling and bypass capacitors. Here there is no question about bypass capacitor, only two coupling capacitors will be included, one at the source side, one at the drain side. Then also we have to do the short circuit of DC sources. So here in this particular circuit we do have the DC source at drain side as well as source side. So we do the short circuit. So RD is connected in between drain and ground and RS is connected in between source and ground. So this is our first step. Second step is draw your AC equivalent circuit with the same orientation. Don't draw with the second orientation. Third step will be find AC parameters. First one is voltage gain. Second one, input impedance, and third one, output impedance. So this is how we will maintain the flow to have AC analysis. Now in the numerical, whenever one question comes for solving AC analysis and to find out voltage gain, input resistance and output resistance, we'll first follow the step number 1 and we will redraw this circuit as I'm doing it right now. If I short all the coupling and bypass capacitors, then your circuit will look like this is your output, this is your input, and here I'm connecting the DC sources as well to ground such that only AC current will flow from the input supply and will get accordingly at the output side. Now we'll try to convert this particular circuit diagram into our usual AC equivalent model. As we have discussed, we will use RPI model for AC analysis of JFET. So सबसे पहले you have to do the modeling of JFET and then connect all the peripherals in the form of resistances and capacitances. Plus minus VGS. This is your GM VGS directly. Dynamic resistance, that is RD, I can say. So this is your source, this is drain, and this is gate. I will connect all the peripherals one by one. At the gate side, gate is connected towards the ground directly. So I will connect this gate to ground. Source is connected to input as well as one resistance RS, which is again connected to ground. So here I can say this is one resistance which is connected to ground, and here I will apply input AC supply. This is resistance Namakaran RS. Drain side pe will be having output voltage as well as resistance RD, which is further connected to ground. So here we will be getting resistance RD, and here voltage, output voltage VO. This completes your AC equivalent model for CG amplifier. Then further, to find out all the parameters in the AC analysis, we will do your 5 fingers. Out of these 5 fingers, we require KCL, we require Ohm's law, we require CDR, VDR in some respect, and another is your KVL. We'll start first by applying KCL at this particular node, such that we will be getting the value of VO in the form of the current or some agent. So let us move further. If we apply KCL over here, one thing you will get to know that this is VGS and this is VI. If you apply the addition of VGS and VI, that should come out to be 0, right? So I can say that VGS plus VI is equal to 0. That is first equation, and from that we will be getting that the relation between VGS and VI. So VGS is equal to minus VI. That is nothing but the one formula which will help us to find out the relation between VO and VI. We'll apply KCL over here. We'll do the Namakaran for this node, that is node number A. One current which is nothing but this current, which is VO divided by RD, right? And another current which is nothing but going from away from node A, which is further divided into two parts. One is GM VGS and another is nothing but this current, which is VO minus VI divided by RD, right? We'll put it in a mathematical form. VO divided by RD plus I is equal to 0. And that I will further open VO divided by RD plus I is further divided into two parts. One is GM VGS and another is plus this is VO minus VS divided by RD is equal to 0. This is same as that of we have done it in CS amplifier without bypass capacitor. If you recollect this particular video, then you will get to know that the relation is near about same. But as we have discussed that from input side we'll get to know that VGS is equal to minus VI, and this is equal to minus Vs. This is because Vs itself is a Vi. Input is applied at the source node. So I can take this in this particular formula. We'll keep VO upon RD as it is. We'll write this VGS in the form of minus Vi. So we'll write this as minus Vi. Here I will write this as VO as it is. Minus Vs will become minus Vi divided by RD. Look at this formula very carefully. I did neglect this particular I and converted VGS in the form of input voltage, such that in this formula we will be getting all things are constant except two parameters variable. One is VO and another is VI, whose ratio is nothing but your voltage gain, and that is nothing but the required one, right? Now if you observe this equation, right, just with little bit of mathematical manipulation we can get the ratio of VO divided by VI. Do this of your own. Take a pause for 2 minutes and calculate the ratio of VO divided by VI in the form of small rd, capital RD, GM. Let's do that. This is the formula of voltage gain. I hope you also have got same answer as I have got here. RD parallel small rd multiplied by 1 plus GM RD divided by RD. Now if RD is tending towards infinity, right, we'll have to put the limit on this particular bracket, because here if we take the limit then we'll be getting RD only, capital RD only, right? So if we apply limit over here then we'll be getting only GM, right, and GM is a very small quantity. Then we'll say that VO upon VI will be limit on RD tending to infinity on the complete bracket, that is RD parallel small rd, and this bracket 1 plus GM into this whole bracket, and this gave me the answer same as that of GM into RD. So this is your formula for voltage gain if RD is not given or RD is very high, near about infinite, right? See the relation of CS amplifier ka gain and this particular gain that we have got right now. Only one change is polarity. As in CS amplifier, 180-degree phase shift between input and output we are getting, but here in CG amplifier we are not getting 180-degree phase shift. Here we are getting 0-degree phase shift, and that's why negative sign is not there in the picture of formula of voltage gain. So here we are ended up with the voltage gain, that is the first parameter. We'll move towards the second parameter. And second parameter is input impedance. Now I want to find out input impedance, right? And the input is applied at the source terminal. Source is again connected to JFET. So here we'll have to think little bit about your 5 fingers. I will again redraw this particular circuit here aside, and then we will simultaneously solve the analysis for input impedance. To calculate input impedance, what I will do? First of all, this Vi divide by the current which is flowing through this particular source, input source, is nothing but, let's say, II, right? And if you apply KVL at this particular point, let's say B, if you apply KCL at this particular node, then we'll be getting one current is coming from GMVGS, one current is coming from RD, and another is going away from the node through RS towards ground. That is nothing but your completely II. If you apply KCL, let's see what we will be getting. IRS is nothing but current flowing through resistance RS. GMVGS is this current, and IRD is nothing but current flowing through small RD. We'll go through this, we'll open up each and every term such that we will be getting the input impedance in the form of Ri is equal to Vi divided by II. So we want only two parameters and rest of all constant in our equation. IRS is nothing but Vi divided by Rs. Is that clear? Yes. Minus GMVGS. Now as I know that this is CG amplifier, this gate is connected directly to ground, VGS is nothing but minus of Vi. So I will treat this as plus, minus will become plus GM into Vi. Okay, and I will say that this term is very small. This term is very small. Though you want to include, you can include, but IRD is nothing but VO divided by your value Vi, and VO is nothing but the value which is coming from this resistance. So IRD, I will open up here, I'll keep this as it is. IRD I will write as it is, and I will write here what's the value of IRD. Okay, VO minus Vi divided by small rd. Okay, somehow I want to eliminate this particular value of VO. How can I do that? VO I can eliminate by just saying that this current is Vi divided by Rs, and the same current is flowing through resistance Rd, right? So I can say that this VO is nothing but this particular current, right, multiplied by this resistance Rd. So we can say that I multiplied by Rd. We'll name this, we'll do the Namakaran, I multiplied by Rd minus Vi divided by small rd. Further, I can change the value of I as, see, this is the value of I, and the same value of current which is flowing through Rd, right? If I say that same current is flowing but in the reverse opposite direction, see, current flowing through Rs is in this direction and this is ground, so current is flowing in this way, but our I direction is towards ground, right? So I can say that the current which is flowing through Rd, that is I, is exactly opposite to IRS. So I can say that what is IRS? Vi divided by Rs. So we can say that I is nothing but minus Vi divided by Rs multiplied by capital RD minus Vi divided by small rd, and this is how we will be getting the value of IRD as is equal to, we'll take minus Vi common and we'll be getting in the numerator RD divided by Rs plus 1 the whole divided by small rd. Very simple. Now everything is constant and we'll get in terms of Vi, right? We'll put this in this equation such that we'll be getting a very concrete value of II divided by Vi or Vi divided by II. Minus minus will become plus, minus IRD is nothing but I kept this term separate. This is because we want to neglect this part. Now why to neglect this part? See, concentrate with this term very carefully. RD upon RS, this is nearly equal to 1, right? Nearly same values. Plus 1 is about 2 or 3, right? But less than 10. RD is very high value, right? So if we take a limit on RD tending towards infinity, this value will become nearly about 0, right? Now if you look at this particular term very carefully, we'll have to neglect. But why? RD is very high. Capital RD divided by capital RS plus 1 is nearly about 3 or 4, not more than 10. So 10 divided by this very high value about mega ohm, I can say that this value will reach out to be in micro or milli, right? If you add this value to this term, that will not make much difference, and that is why we are neglecting this particular term, right? So as far as formula is concerned, after neglecting this particular term, we'll write II divided by Vi is equal to 1 plus GMRS divided by Rs. Clear? We'll reverse this to get the value of input resistance, that is Vi divided by II is equal to, the value is inversed, Rs divided by 1 plus Gm into Rs. The magic is I can take this in the form of parallel combination of Rs and inverse of Gm. How? Let's see. Rs divided by, I'll take this Gm common, so I'll take this Gm common, 1 upon Gm plus Rs. This is in the form of R1 R2 upon R1 plus R2, that is parallel combination of R1 and R2. And what is R1? R1 is nothing but Rs, and R2 is nothing but 1 upon Gm, if you relate these two equations. So now we will be getting Vi upon II is equal to Rs in a parallel with 1 upon Gm. This is your input impedance. Very simple. Now after completing input impedance, we will go for output impedance. While doing analysis for output impedance, we will have to take care that Vi is equal to 0. That means we'll have to keep Vi short circuited and then we'll have to redraw the circuit again. As this Vi is short circuited, Rs has no meaning. So Vi directly connected to ground, and here Rd as well directly connected to ground. So now I can easily get to know that this is small rd, this is GMVGS, but this GMVGS also doesn't have any meaning, right? This GMVGS doesn't have any meaning. Why? This is because VGS is equal to minus of Vi, and that will become 0, right? And if VGS is equal to 0, can I say that this will turn out to be open circuit, right? And this, your complete circuit will be in the form of capital RD parallel to small rd. Here resistance RD and resistance small rd connected in parallel, I will get directly that Ro is equal to small rd parallel to capital RD without any KCL, KVL or any other 5 fingers. So this is how we have completed the output impedance, that is the third parameter of AC analysis of CG amplifier. Once we complete this AC analysis of CG amplifier, we'll again have to go for the 1 or 2 numericals based on CG amplifier, but in further videos. For that, you have to stay tuned for further videos and subscribe, share and like Ekeeda videos. Thank you so much.